Hello! Welcome to a new episode of Solid-State Foundations. In the past videos, we've learned about polymorphs, hydrates, and solvates. Today, we are going to learn about how polymorphs relate to each other. Remember, polymorphism is the ability of one compound to display multiple crystalline structures, each of them exhibiting different properties. To prevent changes during manufacturing or storage, we would normally choose the most stable form of the drug for development. This way, we ensure that no transformation occurs when the drug is exposed to different conditions. But how can we determine which form is the most stable? The simplest scenario is when a compound exists in only two different crystalline forms. In this case, we can encounter two situations. 1. When form A is always more stable than form B. In this case, the transition from metastable form to the most stable form can only occur in one direction, and this will be irreversible. This is called a monotropic system. And 2. When form A is more stable than form B at low temperature, while form B will be the most stable form at a higher temperature. This is an enantiotropic system. In these cases, the transition between the two forms can be reversible. The key here is to establish the transition temperature. Once we know this, we will be able to design processes for the crystallization of the desired form. Understanding how polymorphs relate to each other is as critical as knowing how many polymorphs of a particular compound exist. This will help us design processes and define storage conditions that will preserve the integrity of our chosen crystalline forms. Being able to modify the physical properties of our drug at will is a powerful skill to have. You can choose, for instance, a more soluble form for immediate release and a more stable and less soluble form for an extended release. How cool is that? We hope you find this new section of Solid-State Foundations insightful. See you next month!